join me to throw some money into the water. Now, I'm sure this is a phrase that none of us in this room want to be associated with in any way. However, in certain industries and sectors, such as the abalone industry, where diet costs can cost up to 30,000 Rand a ton, I'm certain that we can agree that the proverbial throwing money into the water is physically unavoidable. Now, that being said, or considering this high diet cost, it's crucial for abalone feed producers to rely on a high degree of water stability. And the benchmark for abalone feeds is typically between 24 or 36 hours that the diets need to remain water stable. This is largely due to the slow growing and passive feeding behavior of abalone to allow sufficient time for the abalone to consume the feed. However, that being said, this passive behavior also relies on a degree of stimulation, especially through olfactory and gustatory stimulation. Therefore, the feeds also require a degree of leaching or some leaching of essential nutrients to stimulate the feeding response of abalone. Lastly, there's also been research showing that a too stable pellet or the use of too much binders that creates a too stable pellet can also decrease the digestibility of abalone feed. Therefore, it's a constant trade-off in the abalone feed industry between having a stable yet too digest or undigestible product and an unstable product which is not utilizable by the animals because it disintegrates in the water too quickly. Now, when we look at water stability, it's typically achieved by two main mechanisms. First and foremost, starch gelatinization, and secondly, through the use of specific binders. Now, when we look at a typical water stability curve, which is expressed as the relative pellet weight after a certain time period, it's typically associated with a rapid leaching period where most of the nutrients leaches out, followed by a slower disintegration phase, where the pellets physically starts to disintegrate. Now, as I mentioned, you want to control the slow release of the nutrients to allow a certain degree of leaching to stimulate feeding, but then prolong the disintegration phase as long as possible. Now, I think it's crucial, we've established the importance of water stability in abalone feed or in the greater aqua feed industries. Now, it is therefore very important when investigating a new ingredient, feed additive, or manufacturing technique to investigate the effect that the specific variable actually has on water stability. Now, that being said, insect meal has become a highly researched topic in recent years, predominantly due to its favorable nutrient content, but also due to the various functional benefits attributed to the ingredient, with a lot of these functional benefits actually being attributed to chitin, chitosan, or chitosan oligosaccharides. Now, these are molecules or polymers that's encased in the exoskeleton of insects and crustaceans, consisting of repeating glucose subunits, glucose subunits with the diacetylcoamine subunits. Now, various research has shown that the biological activity of these molecules actually increases with decreased chain length, decreased molecular weight, and a higher degree of deacetylation. Now, this can be achieved through various mechanisms, with the main one being enzymatic hydrolysis. Now, it's important to note that some studies have postulated that a higher degree of deacetylation actually changes the acetyl binding, binding capacity of these molecules, which changes the water binding capacity and can stimulate these molecules to actually act as a water binder, such as guar gum, which can increase water stability. Now, therefore, we decided, or before we investigated the use of insect meal in abalone feeds, we wanted to see what happens if we include chitinase as a dietary feed additive together with insect meal to see if we can extrapolate some of these or enhance some of these functional benefits that can be obtained. However, before we conducted the main study, we wanted to see whether the chitinase actually can have any effect on water stability due to the structural similarities between amylose, which is the main polymer of starches, and chitin, which I'll touch on later. So the water stability was tested using a standard method of a water agitated water bath composing of 100 compartments, each with a water stone underneath, and feed is then placed in a mesh bag, weighed, placed in the respective compartments, and periodically removed, dried, and reweighed, and water stability subsequently determined. Now, the trial consisted of a standard commercial diet with 6 or various levels of chitinase inclusion and 10 different time periods up to 12 hours with water exposure. Now, when we look at the results of the study, it is evident that chitinase inclusion significantly influenced the water stability of abalone feed, with significant effects already being seen after 20 minutes of water exposure. However, this was only at the 250 grams per ton treatment, and following 40 minutes, we see a linear decrease in water stability with increased chitinase inclusion. It's evident that at higher chitinase inclusions, after 6 hours, there's almost no pellets left in the water and almost no water stability left. When we look at a repeated measures analysis of the results, we see the same observations with significant results already being achieved after 40 minutes of water exposure. And it should also be noted that the control treatment showed very little pellet disintegration, indicating that the diet itself was a highly stable diet, and the effects can therefore only be attributed to the inclusion of chitinase. Now, if we look at possible reasons for the disintegration, we see that we once again see that abalone feed producers rely heavily on starch gelatinization for a degree of water stability. Now, there's a large similarity between most plant polysaccharides, with only small differences between the respective polysaccharides. For example, the difference between cellulose and amylose is only the orientation of the binding between them. Cellulose being alpha beta binding, beta 1,4 bonds, amylose being alpha 1,4 glycosidic bonds, and chitin once again being beta 1,4 glycosidic bonds, with the exception of having an acetylchoamine subunit instead of a hydroxyl subunit. Now, due to these similarities, we see that plant polysaccharides are highly susceptible to degradation by a wide variety of enzymes. For example, the hydrolysis of alpha amylose have been shown to be possible with beta amylase and vice versa. Moreover, various studies have actually shown the high affinity of various plant polysaccharides towards chitin. For example, both beta amylase and alpha amylase have been shown to be highly susceptible or a high degree of affinity towards chitin. It should be noted that no literature exists on the chitinase, the hydrolysis of amylose by chitinase. However, due to the results and the high susceptibility of these plant polysaccharides, it's evident that a degree of susceptibility must exist if we look at the results of the water stability analysis. So in conclusion, I think it's evident that dietary or water stability is significantly influenced by dietary chitinase, likely due to a high degree of substrate ambiguity between the respective substrates and their enzymes. This is a novel mode of action of chitinase that has not yet been previously reported, and the effect of deacetylization of chitin on the effects of water stability has yet to be proven. Thank you.